Welcome. In this video, we'll first see how to create a 3D map of your environment using RTAB-VSLAM and then use that map for autonomous navigation. Let's get started. Now let's set up the robot for 3D mapping. First, start your robot and access the system desktop using VNC remote connection. Click to open the command line terminal on the robot. We need to disable the app auto start service to prevent conflicts. Type the command. Now, launch the RTAB-VSLAM mapping service by entering ROS2 Launch SLAM RTAB-map-SLAM.launch.py and press enter. Wait for the system to initialize. You'll see various ROS nodes starting up, including the RTAB-VSLAM core algorithm and camera drivers. On your virtual machine, we'll launch the visualization tool to see the 3D map being built in real time. Open a command line terminal on the Linux machine. Enter the command ROS2 Launch SLAM Rviz RTAB map launch.py and press enter. Rviz will open, displaying the 3D mapping interface. You'll see the robot's position and the 3D point cloud map being constructed as the robot moves. To build a complete map, we need to control the robot to explore the environment. Open another command line terminal on the robot. Enter the command ROS2 Launch Peripherals Teleop key control launch.py and press enter. When you see the confirmation message, the keyboard control service is successfully activated. Now you can control the robot using these keys. Press W to move forward continuously. Press S to move backward continuously. Long press A to turn left. Long press D to turn right. RTAB-VSLAM stands for Real-Time Appearance-Based Visual, Simultaneous Localization and Mapping. It's an open source library that creates 3D maps while simultaneously tracking the robot's position in real time. What makes RTAB-VSLAM special is its intelligent memory management system. It uses two types of memory: short-term memory for matching current continuous data and long-term memory for detecting loop closures when the robot revisits previously seen areas. This approach ensures that loop closure detection is always processed within a fixed time limit, making it ideal for long-term and large-scale environment mapping. Let me explain the working principle. RTAB-VSLAM uses feature-based mapping, which means it extracts distinctive visual features from camera images. The advantages of this approach include rich feature points in general scenes, good adaptability to different environments, and the ability to use these feature points for accurate localization. Here's how the algorithm works step by step. First, features are extracted from the camera images. Then, the algorithm matches features across different timestamps to detect loop closures. That's when the robot recognizes it has returned to a previously visited location. The data is then categorized into long-term memory and short-term memory. Short-term memory data updates positioning points and builds the map in real time. When data from a future timestamp matches long-term memory data, that information is integrated to improve positioning accuracy and map quality. Here are some important tips for achieving the best mapping results. Reduce the robot's movement speed. The slower the robot moves, the smaller the odometry error, resulting in a more accurate map. Start mapping in front of a straight wall or within an enclosed area. This helps the sensors capture more scanning points initially. Perform a complete 360-degree scan of the environment to ensure comprehensive coverage. For larger areas, complete a full mapping loop before focusing on smaller details. As the robot moves, watch the Rviz display. You'll see the 3D map continuously expanding with colorful point clouds representing the environment. Before moving to navigation, evaluate your map against these criteria. Check that obstacle edges are clearly defined. Verify there are no discrepancies between the map and actual environment. Ensure there are no gray unmapped areas in the robot's motion zone. Confirm the map covers the entire area where the robot will navigate. If your map meets these criteria, you're ready for navigation. Once you've mapped the entire environment, it's time to save your work. Here's the great news about RTAB-VSLAM. The map saves automatically. When you press Ctrl+C to close the mapping command, the 3D map is automatically saved to the system. Press Ctrl+C in each terminal window to close the running programs. Now that we have our 3D map, let's use it for autonomous navigation. Launch the RTAB-VSLAM navigation service by entering ROS2 Launch Navigation, RTAB Map Navigation, Launched POI and press Enter. Wait for the navigation system to fully initialize. This loads the 3D map, starts the localization algorithm, and prepares the path planning system. On your virtual machine, launch the navigation visualization tool. Open a command line terminal. Enter the command ROS2 Launch Navigation, Rviz RTAB Map Navigation Launch PI and press Enter. Rviz will display the navigation interface with your 3D map and the robot's current position. Let's send the robot to its first destination. Click the 2D Nav Goal button in the Rviz menu bar. On the map display, click once at your desired target location. This sets the navigation goal. After confirming the target point, watch the map display. You'll see two paths appear. The line composed of blue squares represents the straight line path, the direct geometric distance between the robot and the target point. The dark blue line represents the actual planned path, the route the robot will follow, accounting for obstacles and navigation constraints. Let me explain these two paths in more detail. The blue squares line shows you the ideal route if there were no obstacles. It's the shortest geometric distance. The dark blue line is the practical solution. The path planning algorithm calculates this route considering all known obstacles from the 3D map, safety margins around obstacles, the robot's physical dimensions, dynamic constraints like turning radius. This visual representation helps you understand both what the ideal goal is and how the robot will actually achieve it. Watch as the robot begins autonomous navigation. The robot follows the dark blue plan path, continuously updating its position using the RTAB-VSLAM localization algorithm. As it moves, the robot compares what it sees with the stored 3D map to maintain accurate positioning. One of the most impressive features is real-time obstacle avoidance. When the robot encounters an obstacle, whether it was in the original map or is a new obstacle, it automatically navigates around it. Watch as the robot adjusts its trajectory in real time, continuously updating its posture and path to avoid collisions while maintaining its goal of reaching the target point. The dark blue planned path updates dynamically as new obstacles are detected. For more complex missions, you can set multiple waypoints. Use the Publish Point tool to click multiple locations on the map. Each click adds a waypoint to the robot's navigation queue. The robot will navigate through each point in sequence, automatically planning paths between them and avoiding obstacles along the way. That completes our comprehensive RTAB-VSLAM tutorial covering both 3D mapping and navigation. To summarize what we learned, in part 1, we created a detailed 3D map of our environment using RTAB-VSLAM's feature-based mapping with intelligent memory management. In part 2, we used that map for autonomous navigation, setting target points and watching the robot plan and execute safe paths while avoiding obstacles in real time. RTAB-VSLAM demonstrates how modern robots can understand and navigate complex 3D environments autonomously. Thank you for watching. If you found this tutorial helpful, please like and subscribe for more robotics content.